welcome to those of you joining us and those of you who have been with us the entire time for our third talk after the what we're calling lunch, coming to us all the way from the University of Goettingen, where it presumably was not just lunch. We have Jialong Deng, who's going to tell us about enlargeable length structures and scalar curvatures. Thank you so much.
Yes, thank you for the introduction, and thank you for allowing me to speak here. Talking about the enlargeable length structures and the scalar curvature. It's all more about the geometry. So first I will define what is the length matrix, and then define the enlargeable length structure, and then apply to the locally catered zero matrix. And finally, I will show that there's a difference between the locally catered zero and the non-positive curvature manifold. And so first I should record that what is the scalar curvature. So given a Riemannian manifold is smooth, and then we can just write the volume of the R-ball, then the scalar curvature appear in here. So the question is that which closed manifold admit positive scalar curvature? And for the three-dimensional, we have by the certain impairment, we know that the manifold must be spherical three-manifold or the S2 closed S1, or the connected sum between each other. And the two-dimensional, that's the section curvature is the scalar curvature. So it's clear. And for dimensional bigger than 4, we have the manifold if the symbol connect and non-spin, then Gromov-Lawson, they show that they admit PSC matrix. And if the manifold is spin, then they carry PSC matrix if and only if here is the alpha invariant vanish. So now our question is that find the obstruction to admit PSC matrix on non-symbol connect smooth manifold. Since the symbol connect for dimensional bigger than 4 is short, but in the dimension 4 there's another story. So I'll only consider in higher dimensions. And this conjecture said that the closed aspherical manifolds carries not PSC matrix. Our result is also motivated by this conjecture. And Gromov-Lawson, they introduced the enlargeables as the obstruction based on the index theory. And later they can relax this spin assumption. And recently, here the Simona and Thomas Schick, they used the Schoen and Yau's results. But here, Schoen and Yau's result, they only prove in archive. So, and haven't been published yet. So they also can show that the closed enlargeable manifold cannot carry any PSC matrix. And those enlargeable mentioned is defined for the Riemannian matrix, and they also need a map is C1 smooth. Here I can define for the length matrix space, and only need the map to be continuous. Then they can find a new obstruction to admit PSC matrix. Let me record that the length matrix means the distance between pair of points equal to the increment of the length of cross join the points. And a closed topological manifold admit length matrix. And the matrix induced by the Riemannian matrix are length matrix, and they are strong. Here means the strongly equivalent to each other. Furthermore, then for the continuous Riemannian matrix, they also induce the length matrix. But the length matrix may be not strongly equivalent to each other. For example, if the one is induced by the Finzel matrix, the other one is induced by Riemann matrix, then they may not be strongly equivalent in general. And here the length matrix can be induced to or lift to the covering space, and the lift is unit the length matrix. Now we can have a definition for the Epsilon hypersuffix. That means given a topological manifold and with complete length matrix, then we can map to the Sn with non-zero degree. Here constant and infinite means that there's a compact subset such that F maps outside the compact subset to the one point. And Sn use the standard matrix. Here the F, they only need to the continuous. And now we can define the enlargeable length structure. That means a matrix D on a closed-oriented manifold. If we call it enlargeable, if there for every epsilon there is an oriented cover manifold induced with induced matrix D tilde, that is the epsilon hypersuffix. And the enlargeable length structure means the strongly equivalence class. That's why I mentioned before that all the Riemannian matrices are strongly equivalent. And the enlargeable Riemannian length structure means that there's a Riemannian matrix on the length structures. And the example is that the Riemannian matrix on the n-dimensional torus. And by the way, we can sort and see that the torus is also an aspherical manifold. And we can also define the enlargeable length structure on the non-oriented manifold, but that's not the point. And the properties is that if there's a ellipsis continuous map F, so S to Y of non-zero degree, and if the dy is an enlargeable matrix, then the ds is also enlargeable matrix. And the two enlargeable matrices are stable under the product. And then we have if the S carry enlargeable length structure, then times S1 also carried enlargeable length structure. And we need to use is the corollary 3 that said that if the dy is enlargeable length structure and S is a closed smooth manifold and is also induced by the Riemann matrix, then the S carry enlargeable Riemann length structure. And we can show that if the manifold is closed smooth and then the carries not p-symmetric in its enlargeable length structures. Here we need a dimensional restrict because our proof is based on Gromov-Sfik ellipsis band theory. They said that if the manifold with the scalar curvature bounded below by n times n minus 1, then all continuum mass for F to Sn, and we need to show that it's non-zero degree and the constant and infinite. Or you can just assume the manifold is closed, then automatically we have this constant and infinite. Then the ellipsis band is uniformly bounded below by the constant C over the square n times pi. And also here we have a conjecture said that the ellipsis band will be the 1, but Gromov, their arm is also want to improve this constancy. But here we use the admit or existence uniformly positive low bound is enough for our proof. And now I will definition what is the length locally characteristic matrix. Then if a geodesical triangle is satisfy the characteristic inequality if it's slimmer than the compression triangle in the Euclidean plane. And a length metric is set to be the locally characteristic metric if every point has geodesic convex neighborhood, such that the every geodesical triangle satisfies the characteristic inequality. Now, locally characteristic manifold is topological manifold. Here, it just assumes it's topological enough in group with a locally characteristic matrix. And Gromov generalized the Hadamard-Cartan theory said that the locally characteristic manifold, their universal cover are globally characteristic manifold. That means that every 2 points can be connected by a unit geodesic length, and every geodesic triangle on it satisfies the characteristic inequality. Thus, a locally characteristic manifold is aspherical. And we can show that locally characteristic matrix that is strongly equivalent to a Riemannian matrix on a closed smooth manifold is an enlargeable matrix. Then by our theory, we can show that those manifolds do not admit the PSC matrix. And the classical non-positive section curvature is enlargeable, is defined by the Gromov and Lawson. But here we can show that all non-positive section curvature are locally characteristic matrices. And if the dimension is 2 or 3, then the manifold admits a locally characteristic matrix. They also imply that the manifold admits non-positive curvature matrix. But there's difference when the dimension is bigger than 3. And we will see that. Rinda and Ferry, they showed the existence of non-positive curvature matrix is not a homomorphism event in general, but existence of a locally characteristic matrix is a homomorphism event. That means that the non-positive curvature matrix depend on the smooth structure. Furthermore, Davis and Hausmann, they construct locally characteristic manifolds do not support smooth structures. So we can see that locally characteristic matrix is we get purely topologically. And Michael Davis, they construct aspherical n-manifold that's not covered by Euclidean space. And if the manifold is admit non-positive curvature, then the universal cover must be the Euclidean space. And Davis and his collaborators construct a closed smooth 4 manifold such that the universal cover is deformation to R4, but the pi 1 is not homomorphic to any fundamental group of the non-positive curvature. That means that the manifold cannot admit non-positive section curvature. And if dimension is bigger than 4, then Davis and his collaborators also construct a topological locally characteristic manifold whose universal cover is not homomorphism to Rn. And furthermore, they also construct that even the universal cover is homomorphism to Rn, but the boundary at infinity is different for Sn minus 1. And we can show that there's some stables if the manifold his universal cover is different for Rn, and n is another locally characteristic manifold. But we need to, the fundamental group is center free. Then the product is also locally Cartesian manifold, but does not support any non-positive curvature matrix. And here, recently, they construct more exotic aspherical manifolds. That's Sapir, in the last year, he constructed an aspherical topological manifold whose fundamental groups closely contain expandants. And Sapir's as exotic aspherical manifold does not satisfy the Poincare conjecture with the coevents. And later, the Osada, he construct aspherical manifold whose fundamental groups contain closely impending expandants. And those exotic aspherical manifolds are constructed by the locally Cartesian matrix, and those matrices are strongly equivalent to the Riemannian matrix. Therefore, the connected sum of a closed manifold with diverse exotic aspherical manifold, and a new example detected by our math carries not PSC matrix. Since before the group of Lawson, they only can show for the Riemannian matrix. And here also there's new example also does not admit PSC matrix. And there's conjecture said that our result holds for all dimensions. Since here we can see that they all can have to, up to now have to be retrieved to the dimensional less than 9. So all have here. But since our proof is based on the minimal hypersurface, so we know that if the dimension of bigger than 9, then there are singular points in there. So, but as we mentioned in the before, that Schoen and Yau they claim they can do for all dimensionals. So if Schoen and Yau's result is true for all dimensionals, then our result is also true for all dimensionals. So that's why we can have these conjectures. And thank you for your attention.
Thank you very much, Jialong. Let's all thank our speaker again, virtually clapping.